Alright everybody, on to the next section. We just talked about in section 1.7. We did a little review back to section 1.7 to introduce some terms and definitions that we're going to use while we're talking about circles. Today I want to go over section 6.1. It's the first section in chapter 6. And chapter 6 is all about circles. 6.1 specifically starts to talk about some of the properties associated with a tangent to a circle. And I was very excited to see that the book used this picture to represent a tangent line. It said that the two penguins right here, their heads are tangent to each other because their heads are only touching at one point. So I thought that was pretty cute. Excited to see other people using penguins. As you guys know that I like penguins quite a lot. So let's do a quick little review as we build into our first tangent property. And what I'm going to do is I'm going to talk through the properties of tangents. And if you guys will look in section 6.1, it gives you two conjectures that you need to be familiar with. So I'll go through the properties, we'll talk through them and talk about them, and I'll let you go into chapter 6.1 and look at the two conjectures that you need to fill in. Make sure you have those conjectures in your notes, you understand the properties behind them, you understand the concepts that I'm talking about on the video as well. So first things first, let's draw ourselves a circle. It's a good place to start, and Geometry Sketchpad does it much nicer than I could do freehand. So I've got this circle, and we name a circle by its center. That's circle A. And I can put a point on the circle right here. We'll call that point B is on the circle. And remember, any point on the circle is equidistant from the center. We could call a segment from the center to any of its points a radius. So here I've got radius AB. Now in order to talk about tangent properties, we have to have a tangent line. But I'm going to start with this first. Hopefully you guys remember that's called a chord. I've got chord BC. Now one of the things that we didn't introduce in the terms and definitions in our review is the idea of a secant line. Now a tangent line touches a circle only once, but a secant line goes through a circle. And if a line goes through a circle, it's going to go into it. It's got to come back out of it at some point. It's going to touch the circle 2 times. So it'll have 2 points on the circle. So right now I've got secant line BC. I've got chord BC as well, this line segment. And I've also got radius AB. Let's check out what happens if I look at the measure of angle ABC. So I've got angle ABC. Right now it's 44 degrees. But you know, if I bring C, if I bring it down here, the angle gets a little bit smaller, and it gets smaller and smaller. The angle is about 11 degrees here, 11 and a half. Well, let's see what happens. If I can get further away from B, I could also get closer to B. And as I round the circle and on B, I get closer. My chord gets smaller. My angle gets larger. So let's approximate a tangent line here. Let's make this line, we'll call this line line J. Let's say I made line J tangent to circle A. I'm just move that name out here a little bit. As point C gets closer to point B, I'm going to try to get it right on top. I'm trying to get it as exactly on top as possible. As point C gets closer to point B, I'm approximating a tangent line. Look what's happening to my angle measure over here. It's getting bigger and bigger. You guys can all probably make a good conjecture right now. When I get C right on top of B, that angle is going to be about 90 degrees. Get out of there, Jay. Now, as I move past B, look, oh, there it is right there. I got it right on top. So now, this line, line J, is tangent to circle A. It passes through B. I put point B and C on the exact same location now, and the angle formed is 90 degrees. I've made a right angle there. Let's see what happens if I come off of there. If I continue to the right, I get lower and lower and less and less. So my first property that I can know about a tangent line is that a tangent line, did it again, a tangent line is perpendicular to the radius through the point of tangency. So what do I mean by that? Or the radius from the point of tangency. So what I mean is, here's a radius, AB, and now that I've made line J tangent, point B is the point of tangency. So radius AB is a radius at the point of tangency. And the line that is tangent to circle A is perpendicular to this radius. So anytime I have a tangent line, if I draw a radius to the point of tangency, I make a right angle. That's the first thing we're going to learn about tangent properties. So now that we know that, let me get rid of that line, and let's make a permanent tangent line. I'm going to construct a perpendicular line through point B. So since point B is on the circle and AB is a radius, if I make a perpendicular line through point B to segment AB, it becomes a tangent no matter where I move it. Now let's put another point on the circle. See what it names this guy. This is point D now. And let's make another radius AD. Now let's take and make another tangent line, but this time with a point of tangency at D. If I construct another perpendicular line, I've made another tangent line here. And now I have a tangent line K and a tangent line L. But look what happens at these two lines. They intersect outside of the circle. Let's drop a point right at that point of intersection. We'll name that guy point E. Now my second property of tangent lines has to do with the segments that are formed when I make a tangent line from an outside point. So how many lines can be tangent from point E to the circle? Well, there could only be two, right? Only ED and EB. If I move the point down here, if I made a point here and then constructed a line from that point to point E, look, it's going to pass through the circle. If I tried to make a line from point E, if I tried to make a line from point E to anywhere else on the circle other than D or B, it's going to go through that circle. So every point not on a circle has exactly two lines that are tangent to the circle passing through it. In this case, we've already identified those two lines. Line ED and line EB, or line L and line K. Now I can also say that this line segment BE, is tangent to the circle, and segment DE is tangent. So just this portion that's measurable here is also tangent. It's only going to touch the circle one time. So what do we think is true about segment EB and ED? Two tangents from the same external point. Let's see what happens when I look at the distance of those two. And some of you guys are probably already there. You probably look at it and see that they look congruent. But let's confirm it. Hey, look at that. They are in fact congruent. The two tangent lines from an external point to a circle form two tangent segments that are congruent. So segment EB is congruent to segment ED every time. Now it doesn't matter where I move point B. If I move point B, the tangent line L intersects this other tangent line a little further away. But these segments are still going to be congruent. If I move D back up, same thing. Doesn't matter how close they get, how far away they get. Any two tangent segments from the same point, not on a circle, the same point outside a circle, will be congruent. And let's do another little review on polygons and on quadrilaterals here. What kind of figure did I make here? Figure ABED is a quadrilateral. But it's a quadrilateral with these two segments are consecutive, these two sides are consecutive and congruent, and these two are both radius. So since they're both a radius, they must be congruent because all radii are congruent in the same circle. So these two are consecutive congruent sides. So this quadrilateral has a pair of, or has two consecutive congruent sides. I've just made a kite. Let's go one step further here, ladies and gentlemen. Let's check this out. These are my non-vertex angles. In a kite, the non-vertex angles are congruent. And these are congruent, but not just are these congruent, they're also 90 degrees each. And if I look at the polygon sum theorem, it says that the interior angles, the measures of the interior angles of a quadrilateral sum to 360. So if I know that this is 90 and that's 90, all that's left is 180. Which means that in this circumstance, if you ever see this figure again, you can know that this angle, a central angle on the circle, and this angle, an angle formed outside the circle, are going to be supplementary. Every time. Let's double check it. Let's use Sketchpad to measure the angles. So angle BED is 40.21. What about this central angle? Angle angle BAD. See if we can make them a little nicer. I can't get the decimals to go away. But if you add those two up, you get to 180 degrees. And knowing that this central angle BAD is 139.43 degrees, let's see what arc BD's measure is. It's also 139.43 degrees because the measure of an arc on a circle is equal to the measure of the central angle that intercepts it. Alright, ladies and gentlemen, that's 6.1. Come see me again shortly for a nice video on 6.2. Remember to go back into your book, write in your notes the conjectures that are associated with 6.1. There are two of them. And with the knowledge we just talked about with this video, you should be able to fill in both of them.